23. Okay, good morning, all of you. So, last class we discussed about simply supported beam with point load, simply supported beam with UDL, and simply supported beam with UDL and point load. That is combination of two loads. Okay. So, any doubts from simply supported part? Any doubts from simply supported part with point load with UDL? How to draw shear force and shear force and bending moment diagram? Any doubts? Simply supported beam with UDL and point load. I'm sharing my screen. Let me know if it is visible or not. Okay. So today we'll discuss your cantilever beam. Okay. Cantilever beam with point load. First we'll see cantilever beam with point load.
In this tutorial, I will show and B.
So screen is visible? Is my screen is visible?
Yes, ma'am.
Okay. Thank you. Students join. 26. Okay, fine. We can start. So today we'll discuss a cantilever beam. This is a cantilever beam which is fixed at one end and free at one end and free at another end. Okay. So we'll discuss today cantilever beam with point load, with the UDL, then with UDL and point load. Okay. And with here only one point load is given. We'll discuss more next problem with two more point loads. Okay, so let's start our class. So this is a cantilever beam of span L and a load is applied of W, which is applied at the free end. So we'll see how to draw shear force diagram and bending moment diagram for these kind of beam. Okay, so let's start.
And B carrying a point load at end B. Consider a section XX at L to draw the shear force and bending moment diagram for a cantilever beam carrying a point load at its free end. Consider a cantilever beam of span L fixed at end A and free at end B carrying a point load at end B. Consider a section XX at a distance x from the free end B and consider the right portion of this section.
So I
The
want to
shear
discuss
force
here.
at this section.
Suppose you have here you have one section A and B. So you can take a section of XX between A and B from the left side or the right side. It's up to you. Okay. In cantilever beam, you can take from it's up to you. You can take a section. You can take a section from this direction or this direction, and it is only one section A to B. So one section will be enough. Suppose in question one more section is given. Let me take an example. Suppose a cantilever beam is given. A cantilever beam is given. One load is here. This is A. This is B. Suppose I have another point load and I have a section of C here. So in that case, what you do, consider a section here and one more section. So there will be two sections between A to C and C to B. Okay, so now I have only one section with A to B, so I am considering one section XXX will be enough. Understood? Suppose, and again another, not in cantilever, in simply support also, number of section will give you number of that number of section you have to take, segments, number of it will depend upon the number of segments. Okay, suppose I have, this is the D. Suppose this is a simply supported beam, I have 3 segments, so I have to take 3 sections to find out the shear force and bending moment. Okay, in next problem you will understand this part, but I want to discuss here. So understood? So based on the number of segments, you have to take the sections for the shear force and okay? Okay, let's start.
Section will be equal to the resultant of forces acting on a right or left portion of this assumed section as per the definition of shear force, according to which the shear force at any section XX is equal to the summation of all the forces acting either to the right or to the left of that section. But the resultant force acting on a right portion of this section XX is W, which is acting in downward direction, and since this W lies in right portion of XX, it will be considered positive as per the sign conventions of shear force diagram, which we have already gone through in our previous tutorials. Hence this shear force at section XX is positive. Let Fx be the shear force at this section XX, hence Fx will be equal to plus W. Since W is the resultant of forces acting on right portion of this section XX, the resultant is positive since the shear force at this section XX has to be positive as per the sign conventions of shear force diagram. Now for drawing the shear force diagram, we will start from drawing the span AB of the cantilever beam. And now we understand that at point B the shear force will be equal to plus W, and since we have derived already that shear force at any section between point B and A will be equal to this plus W, so we will draw this plus W to some scale, and this will remain constant from B to A. Hence this will be our shear force diagram. To make it clearly visible for you, our shear force diagram will look something like this. This is the baseline, and since the shear force is positive, that's why our
So if you see for the shear force diagram, what they did, they considered a section, okay, XX at a distance of x from the free end. So now for the shear force, at this section, how much is the shear force? Only this upward force W. So they have considered the upward force as positive, so it will be positive W. So if I consider a section, so if I want to know what will be the shear force here, so it will be the same shear force, only W, because there is no any external forces. Okay, there is no any external forces. In cantilever beam, there is no reaction forces. Their reaction forces is zero. So the only the shear upward load will be W. So the only shear force is W. If you consider a section here, the only shear force will be here. So at A also it will be, at A B also it will be W, and at A also it will be W. So my shear force diagram will become like this. Okay, this will be my shear force diagram. Positive because I have got positive value, so it will be upward. So if you draw, so this is my shear force diagram. Okay, from the baseline, as the value is positive, so it is upward. Now for the bending moment diagram, again I am taking a section of XX at a distance of x. So what is bending moment? For bending moment, we used to take force into distance, right? So now here force is W, and the distance I can take x. This distance x can be anything between L, right? So my movement will be W into x. So if I take a consider section here, if I consider a section here which is at a distance of x meter from the free end, so again my movement will be same, W into x. Understood or not? Force into distance. So between A and B, any section, I can take any section, I can take section here, I can take section here at a distance of x. The value of equation will be same. It will be w into x. Again, it is giving a clockwise movement. So in this question they have considered a clockwise movement as negative. So take so bending moment will be negative, and your drawing will be, this is the sign convention they have considered. So your bending moment will be negative. So if you replace x with 0, so you will have 0 bending moment at B, and if you replace at A x is your how much? L, right? L. So if you replace that x with L, so your bending moment will be W into L. So see the video, then you will understand more. Okay, let's start.
Let mx be the bending moment at section xx. The bending moment at xx will be given by mx equal to minus times this point load w into this distance x from section xx to this point load w. The bending moment will be negative as the moment due to load w will be clockwise for the right portion of this section xx as per the sign conventions of bending moment, according to which the beam will bend in a way that convexity will be at the top. From this equation mx equal to minus wx, it is clearly evident that the bending moment at any section between A and B is directly proportional to the distance of section xx from free end B, which means as we go from B to A, the bending moment will increase and this bending moment will be negative. At x equal to 0, that is at point B, bending moment will be 0. And at x equal to L, that's at point A, bending moment will be equal to minus WL. Since at point A x will be equal to L, hence substituting this x equal to L in the bending moment equation, we will get the value of bending moment at A equal to minus WL. Hence, bending moment follows the straight line rule, since the derived equation for bending moment relates with the equation of straight line, which is y equal to mx, but here in this case we got a negative slope as minus w. So the bending moment diagram will be drawn below the baseline. Now let's try to draw the bending moment diagram. We will start from drawing the span AB. Now we know the bending moment at point B is equal to 0. So we will mark this point as 0, and the bending moment at point A is equal to minus WL. So we will draw WL to some scale, but since this is negative, so we will draw it below the baseline. And now we will join these 2 points. This will be our resulting bending moment diagram. For a clear visibility, the bending moment diagram will look like this. This will be the baseline and WL will be drawn below the baseline to some scale, and the bending moment diagram will be negative. So this was all negative. At x equal to 0, that is at
Okay,
point L.
so understood the bending moment part.
Since
Any doubt from the bending moment? As you have got negative bending moment, that's why bending moment was downward. Okay. Here bending moment is 0. Here you have got negative bending moment. That's why it is minus W into L. Why students are joining now? Okay, I'll share the next problem. Okay.
In this tutorial, I will at points A, B, C equal to this from point D. We need in order to shear force and bending moment.
So in this problem, we'll see a cantilever beam with three different loads, different loads or point loads: 50 Newton, 100 Newton, 200 Newton. Okay, so we have one, two, three sections. So we'll take three sections. Okay, so let's see this problem, then we'll discuss again. Okay.
Diagram of the given cantilever beam carrying point loads at different locations. In order to draw the shear force diagram, we need to calculate the values of shear force at points A, B, C and D. And we will start from point D. So shear force at point D will be equal to this point load 200 Newton, and shear force just to the right of point C will also be equal to 200 Newton, since shear force between point D and C will remain constant since there is no load acting in between. Now shear force just to the left of point C will be equal to summation of all the forces in the right portion of this point, which will be equal to 200 Newton plus this 100 Newton equal to 300 Newton. And shear force just to the right of point B will also be equal to 300 Newton. Since shear force will remain constant between point C and B because there is no load in between C and B. Now shear force just to the left of point B will be equal to summation of all the forces in the right portion of this point, which will be equal to 200 Newton plus 100 Newton plus 50 Newton equal to 350 Newton in total. And shear force at point A will also be equal to 350 Newton because shear force will remain constant between point B and A due to absence of any other load. Now for drawing the shear force diagram, we will start from drawing the span of the beam, and as we calculated, shear force at point D will be equal to 200 Newton. So we will draw 200 Newton to some scale at point D. Since the shear force is constant between point D and C, so we will draw a straight line between these 2 points which is parallel to the span, and shear force just to the left of point C is equal to 300 Newton. So we will draw another 100 Newton above this point to make it 300 Newton. The shear force between point C and B is constant and equal to 300 Newton. So we will draw a straight line between point C and B which will be parallel to the baseline. The shear force just to the left of point B will be equal to 350 Newton. So we will draw 50 Newton about this point to make it 350 Newton. And since the shear force between point B and A is constant, so we will draw a straight line between B and A which will be parallel to the baseline. And now joining these 2 points, we will get the resulting shear force diagram. For a clear visibility, the shear force diagram will look like this.
So for the shear force, what they
100
did,
Newton plus 50
have you seen?
Newton.
They have
There
taken
is
some
to the
points.
right D and B.
For the first
Shear
section,
force just
that
to the
means shear force at D. So at D only a point load is acting 200 Newton. So shear force at D will be 200. Now from C to D, it will be same shear force. Okay, from the shear force acting at D will be same for C to D. But at C, your shear force will be 200 plus 100. Let's see this one. The next step, shear force at C will be 200 plus 100. That means this force and this force. Okay. Now from B to C, same shear force will be acting. That is 300 here at C. Shear force was 300 Newton. So from this C to B, your shear force will be same. Now at B, your shear force will be 200 plus 100 plus 50 Newton. If you see, shear force at shear force at B will be this one, 200 plus 100 plus 50. So 350 Newton. Now the shear force between A and B will be throughout the same, which will be 350. So with this point, with this different shear force, we can draw shear force diagram like this. Okay. First, my shear force was 200 at D and between C and D. Okay. So this is the shear force diagram for this beam. Have you understood? Any issues? Any doubts? If you have any doubts, write in the chat box. Okay. I'll move forward. Okay, let's now move forward to the bending moment. Okay.
Moment diagram, we will calculate the values of bending moment at all the 4 points A, B, C and D. The bending moment at point D will be equal to 0, and the bending moment at any section between C and D at a distance x from point D will be given by mx equal to minus times 200 into x, which follows a straight line law, which means the bending moment diagram between C and D will be a straight line but with a negative slope. The bending moment at point C is equal to minus times this 200 into 4 equal to minus 800 Newton meter, and the bending moment at any section between B and C at a distance x from point D will be given by mx equal to minus times this 200 into this distance x minus 100 into this distance, which will be equal to x minus 4, and the negative sign is because of the sign conventions of bending moment diagram. Hence this equation also follows the straight line rule, which clearly indicates that the bending moment diagram between point C and B will be a straight line but with a negative slope. At point B, x will be equal to 8. So bending moment at point B will be equal to minus times this 200 into 8 minus 100 into this 4 equal to minus 2000 Newton meter. The bending moment at any section between A and B at a distance x from endpoint D is given by mx equal to minus times this 200 into x minus 100 into this distance, which will be equal to x minus 4 minus 50 into this distance, which will be x minus 8. And hence it follows a straight line law, which clearly indicates that the bending moment diagram between A and B will be a straight line. At point A, x will be 10. So on substituting value of x in this equation, we will get the value of bending moment at point A, which will be equal to minus times 200 into 10 minus 100 into this distance, which will be 10 minus 4 minus 50 into this distance, which will be 10 minus 8. So we will get in total minus 2700 Newton meter. So we got these values of bending moment at different points for drawing the bending moment diagram. For drawing the bending moment diagram, we will start from drawing the span of the beam. And since the bending moment at point D is 0, so we will mark this point as 0. As calculated, the bending moment at point C is equal to minus 800 Newton meter. So we will mark this point as minus 800 Newton meter to some scale, and we will join these 2 points by a straight line, since this span follows the straight line rule. Now the bending moment calculated at point B is equal to minus 2000 Newton meter. So we will mark this point as 2000 Newton meter to some scale below the baseline, and join these 2 points by a straight line, since this span BC follows a straight line rule. The bending moment calculated at point B is equal to minus 2700 Newton meter. So we will mark this point below the baseline as 2700 Newton meter to some scale and join these 2 points by a straight line since AB follows a straight line rule. Now enclosing the diagram by joining these 2 points, we will get the resulting bending moment diagram. For a clear visibility, the bending moment diagram will look like putting value of x.
So for the bending moment, what we have to do, same like shear force, we have to take the sections. Okay, we have to take a section here. Let me note. We have to take a section here, here, and here. Okay, we'll take three sections. So for the first section, let's consider at D there is no distance, so bending moment will be 0. Now for C to D, let's take a section. Let's take a section of X. Let's take a section XX at a distance of X meter. Okay. So what will be the bending moment? Force is 200 and distance is X. So it will be 200x. Okay, so bending moment from C to D at a distance of x will be force into distance. So if you see, it is 200x. As we have considered the clockwise is negative, so minus 200x. Understood? Now let's consider another section. Now bending moment at C. So for the C, you can take a section. We know C is at a distance of 4 meter from the free end. So we can write 200 into 4. So this is the bending moment at C. But bending moment between C and D will be 200x. But at C, as we know the distance, so we can replace this x with 4 meter. That's why the bending moment is or 800 Newton meter. Again, it is in downward direction, clockwise direction, so they have considered the negative. Now bending moment between B and C. So I can take a section between B and C. Let me draw a section between B and C. I have drawn a section of XX at a distance of x from the free end. Okay, so I can write minus 200 into x. This is the value minus 200 into x. Again minus this 100. The whole distance is x meter and we know this distance is 4 meter. So how much this will be? How much this will be? Tell me. If the whole distance is x meter, this distance is 4 meter, how much this will be the distance? Reply. It will be x minus 4. The whole distance is x meter, this part is 4 meter, so this will be x minus 4 meter. So this 100 Newton is acting at a distance of x at a distance of x minus 4. So 100 into x minus 4. So this is the bending moment equation between B and C. Okay. But at B, if you need to find the bending moment at B, what you can do, you can replace this x value with 8. Let's see the next step. Bending moment at B. So they have replaced the x with 8. So this is the bending moment at B. Understood? Now the last section I have to take between A and B at a distance of x meter. So what will be my bending moment? 200 into x minus 200 into x minus 100 minus x minus 4, 550 into x minus 8. So let's see. So this is the bending moment equation between A and B. So if I need to find the bending moment at A, you can replace with distance 10 meter. Any doubts? So if I place this, these are the different bending moments at different points. So draw the bending moment diagram with these values. You'll get a straight line. As the values are in negative, so it is in downward direction. This is the bending moment diagram. And it is following a straight line law. But when see when you the load is replaced by UDL, you will get a parabolic. So with UDL, you will get parabolic bending moment diagram, and with point load, you will get straight line. So any confusion from this part? Um, any confusions? Ivan, you wrote X. How will I understand? Any doubts? Only Raju replied. Okay, you can write your roll numbers in the chat box if you don't have any doubts in this. Write your roll numbers. Don't leave the class, okay? Just write your roll numbers. Anyone left to write their roll numbers? Okay, I'll share the syllabus for second session exam today, okay? It will be from 7th of this month. So prepare well. Anyone left? Last was 114. Sure. I'll call out the roll numbers, check once, okay? 51, 75, 76, 98, 85, 52, 103, 82, 95, 90, 84, 80, 74, 88, 73, 94, 102, 120, 61, 92, 68, 67, 83, 70, 53, 79, 86, 77, 107, 81, 51, 87, 91, 71, 93, 100, 66, 116, 114, 109. Okay, see you in the next class. I'll text in the group, then join for the next class. Okay, thank you.